A few weeks ago, this was my shredder. In our last episode, we identified the problem, made the necessary measurements, and were introduced to FreeCAD. In this episode, we'll start FreeCAD, plug those measurements into the gear workbench, and let that workbench work its magic by creating our gear. For the moment, I'll assume you'll already have what you need and you have opened FreeCAD to its opening screen. At this point, you can do it the hard way by going to the top toolbar and selecting File, then selecting New, but this is doing it the hard way. It's far easier to go to the Start New Project menu and clicking Part Design. This will open a new menu labeled Unnamed. Before we go too far, we'll need to go to the toolbar and select File and Save on the upper toolbar. Once you click Save, you'll be asked for a name to save your part. For this project, we'll name it Shred Gear, then click Save. Before we go much further, I'd like to suggest that you arrange all of your measurements for each gear in a table. For each gear, you'll need a column for height, number of teeth, outside radius, and optionally beta angle as well as pressure angle. Once again, we're now back at the Shred Gear project screen. On the left, you'll see a menu titled Start Part. Click on the Create Body option. Then click on Create Sketch. You'll now be taken to another menu. Click on XY Plane, then click OK. You'll now notice that your drawing space has been populated with a drafting grid. The first thing we'll do is create a cylinder which will ultimately serve as the center hole for our compound gear. Once again, please pay attention to the cursor. On the toolbar, you'll want to select the circle icon. As you move your mouse to the drawing section of the screen, you'll notice the circle icon along with a small white cross. As you move the small cross over the red dot in the center, the red dot will turn white. When this happens, left-click the mouse button. This will cause the center of your circle to anchor at 0x and 0y on the coordinate in the drawing space. Also, for this case, the center of the circle will also be anchored to the 0z coordinate as well. As you drag your mouse, you'll notice that the circle will get bigger as you move further away from the circle center. Also, there is a number in dark blue which also gets larger as the circle grows. This number represents the circle radius. Adjust the circle such that the number is very close to 3. At that point, left-click your mouse. It doesn't have to be perfect. We'll fix that in a moment. But first, I want to discuss the meaning of this. The diameter of the steel shaft on the shredder measures 6 millimeters. I know it would be tempting to use the gear hole size we obtained during our measurements, but this gear has been in service for a while. Therefore, it is likely to have a much larger center hole than when it was new. Obviously, we'll need some extra clearance in the gear hole so it will move freely on the shaft. 5/1000ths of an inch is a good figure for work such as this, but since we are working in millimeters, 0.13 millimeters is close enough. Additionally, we'll need to compensate for the fact that 3D printers lay down a wider print ribbon than the size of the print nozzle. For 0.4 millimeter nozzle sizes, a good assumption is 0.5 millimeter wide print ribbon. Hence, for a 6 millimeter shaft, we'll need to add an additional 0.13 millimeters plus 0.5 millimeters to the shaft diameter. This results in a shaft size of 6.63 millimeters. Heading back to the drawing area, we'll now left-click on the perimeter of the circle. Notice that the circle has now turned green. On the toolbar, there is another icon which looks very much like a circle, except it has a radius line through it. You'll now notice a dialog box pop up in our drawing area. You'll now need to enter 3.12 millimeters in the radius dialog box, which is obviously half the value of the 6.63 millimeters which we computed for the diameter of the shaft. You'll notice that the size of the circle has changed slightly to its final value. On the left side of your screen below the Model and Tasks tabs, you'll notice a Close button. Click on that button. Again, click on the circle in your drawing area. You'll notice the circle again turned green. Follow my cursor and notice that I left-click on the pad icon. On the left, a new menu has popped up asking for the length of the pad. Enter the overall height for both gears, which you previously measured. For my gear, this was 32.84 millimeters. Press Enter, and by now notice that the center of the circle has turned white. That's because our circle is now turned into a cylinder. Watch as I move my cursor and click the perspective view. We have indeed created a cylinder. Moving again to the top view and left-clicking again, we are returned to the previous view. On the left side of the screen is a Labels and Attributes menu tree. Left-click on the pad label. There is now another menu below of which there is a label titled Visibility. Left-click on Visibility and notice the area to the right has changed to a drop-down menu. Left-click on that menu and left-click on False. You'll now notice that the cylinder has disappeared from the drawing area. It's not gone, we just temporarily hid it from view. To get rid of this menu, just click on an empty area in the Labels and Attributes tree. We are now ready to design the pinion gear. One thing to note regarding pinion gears is that the base or root of the gear tooth needs to be cut back. This is to keep the tooth tip of a larger gear from colliding with the base of a pinion tooth. I'll show you how to do that in a moment. By the way, it's a good practice to consider any gear with 12 teeth or less to be a pinion gear. We'll now need to go to the top of the toolbar drop-down menu, which is now labeled Part Design, and left-click on it. This will open a drop-down menu. We'll want to left-click on the gear label. This will now open our gear workbench. Watch the cursor as I left-click on the involute gear icon. You'll notice that a gear has popped up in the drawing area. I'll now click on the gear label in the Labels and Attributes tree. You'll notice that another menu has again popped up below the tree. At the bottom of this menu are two tabs. Left-click on the tab labeled Data. You'll see that the information above has changed. We'll now want to left-click on the box labeled Teeth. You'll notice that the number of teeth has also been highlighted. Change that number from 15 to 9, corresponding to what we measured for our gear. You'll now notice that the gear in our drawing area now has 9 teeth. Next, you'll want to left-click on the Undercut label, then left-click on the box next to it. In a moment, you'll notice the lower part of each gear has been cut away. The next entry below Undercut is the pressure angle. Left-click on this and in the adjacent window, enter 30 degrees. In a moment again, you'll notice the gear teeth have gotten thicker at the base and now come to a point at the tip. For our next entry, we'll need to enter the gear height. This entry is further up the menu. As before, left-click on Height and change the value to 20.5 millimeters, which we calculated during our measurements. As you may have guessed, our gear is sitting on the surface of our drafting pad. However, we need this gear to sit atop the helical gear. Therefore, we need to raise it on the Z-axis. To do this, go to the very top of this menu and left-click on the black arrow before the placement label. This opens up more menus. Again, left-click on the black arrow in front of the position label. There is now a submenu with 3 coordinates. Left-click on Z and change that value to the height of the helix gear. Below the Z label, you want to change the label from involute gear to pinion gear. The last thing we need to set is the outside radius of our gear. If you've ever looked in a gear catalog, you've probably noticed that there is no specification for the outside diameter. Well, that's because gears are not specified that way. The gear size is referenced to an imaginary dimension known as the pitch circle. The size of this circle lies somewhere between the outside diameter of the gear and another circle which lies at the base of the gear teeth. There are some rather complex formulas for determining the size of this circle, but we're not engineers designing a gear from scratch. We're just trying to duplicate the damaged gear we have. What we need to do is create a reference circle. First, let's switch views to perspective view. Next, we'll select the top of the gear, then we'll click to the sketch icon. As you can see, we now have a sketch attached to the top of the gear. We'll again set our view to top and center our drawing by pressing the middle mouse button and dragging our gear to the center of our drawing. Next, we'll select the circle icon and left-click when the red dot in the sketch turns white. Again, as we drag the mouse, the radius of the reference circle will change. Left-click the mouse button when the blue numbers are approximately equal to 12 millimeters. You may need to rotate the center mouse button down to be able to see the entire drawing. As before, we'll left-click on the circle perimeter, then left-click on the radius button. We'll then enter 11.96 millimeters, which was the value we measured previously for our pinion gear outside radius. Looking at the circle, it becomes obvious that our gear size is much too small. In the Labels and Attributes tree menu, left-click on the pinion gear label. The same gear data menu opens up below. This time we'll be concerned with the entry labeled Module. The size of a gear is specified by two values. According to convention, if you're specifying the dimensions in inches, you would specify the gear size as diametral pitch. If you are using millimeters, you would specify the gear size as module. The two specifications are related to each other. In fact, to find the diametral pitch, if you know the gear module, you simply take 25.4 and divide by the module value. Although this seems somewhat repetitive, an engineer will know at a glance that the gear is metric simply by designating the size as module. So what is this module value anyway? Module is defined as the diameter of the pitch circle divided by the number of gear teeth. As a first approximation, we'll simply take our outside diameter and divide by the number of teeth. This is done by taking 2 times the 11.96 millimeter gear outside radius and dividing by 9 teeth. This would give us a module value of 2.66. Let's try this by entering this value for the gear module. As you can see, this value is much too big. Let's try a smaller value, say 2.1. Now the gear is much closer to our final size, but it's still too small. Enter a value of 2.17. This time the gear tips are just touching the circle. This is the value we'll use for this gear. In our drawing, you'll likely see a yellow artifact of the original gear. In our tree on the left, you'll see an entry titled Copy Involute Gear. It's part of the geometric description the program needs, but it's annoying to look at. Just left-click on that entry and set the visibility to false. Just like the cylinder before, we'll hide the gear and circle sketch for now by setting their visibility to false as well. Now it's on to the helical gear. As you can see, we've already gone to the gear workbench and created much of the helical gear already. As is the case for most spur gears, the configuration of this gear is largely identical to that of any gear. The 3 principal values we set are the gear height of 12.34 millimeters, the number of teeth to 37, and as you can see, we already went through the guessing process to determine the module value of 1.23. Additionally, we set the gear label to helical gear. Since the pressure angle of this gear is 20 degrees, there was no need to change the default value given by this workbench. Before we finish, there is one last parameter to set. Switching to the perspective view, we'll now need to set the beta angle to 25 degrees. We're now finished with the construction of the helical gear, and it's now time to put it all together. First, turn on visibility of the pinion gear. Next, it's time to turn the visibility on for the shaft cylinder. Switching to the part workbench, we'll left-click on the geometry icon. On the left, a new menu will appear. At the top of the menu, we'll select Difference. For the first shape, we'll select Pinion, and for the second, we'll select Pad. Then we'll left-click the Apply button. As you can see, there is now a shaft hole in the pinion gear. If you were to look down the shaft hole, you'd see that there still is no hole in the helical gear. Therefore, we'll now set the first shape to helical and left-click Apply again. We'll now left-click the Close button. This finishes the construction of our gear. At this point, it's a good idea to click File and Save to save our project. We're now at a crossroads. If we have access to machine tools and wanted to make our gear assembly out of metal, we could go to the Path Workbench. Here, the necessary tools exist to create a program that a computer-controlled machine would understand. While this is tempting to do, there is one factor which would make this choice far too expensive. The problem lies in the matter of gear cutters. Off-the-shelf gear cutters come in standard module values. Since our module values are anything but standard, this would push the cost of this project far beyond the cost of just replacing the entire shredder. Hence, we'll produce our gear out of plastic using a 3D printer. In the last and final part of this series, I'll show you how to use the Mesh Workbench to generate an STL file that any 3D printer can understand. Part 3 will be up in a day or two. Depending on when you view this, Part 3 may already be up. In the meantime, please hit the subscribe button in the lower right corner to receive automatic notifications. In the near future, we'll be planning a lot of projects to help you repair the things that break, which manufacturers no longer support. In the meantime, remember this: it's seldom necessary to buy new if you're empowered to create the parts you need.